Hello and welcome to module 11 lecture 1 part 2 of navigation. It's a warm day in Chennai, so I hope I don't sweat too much when talking now. Alright, so in the previous lecture we saw some basics of navigation. So we discussed some really interesting story of Alexander's march, how desert ants search for food, how to do celestial navigation and so on. We briefly discussed dead reckoning, celestial navigation, coastal navigation and something about GPS and other things, although that was very brief. What we are going to do today is to dig a little bit deeper into the first cut equations of dead reckoning, and we will see why reference frames are very important. Okay. In the next lecture, I will actually show to you the kind of errors that are induced because of dead reckoning. All right, and those errors are primarily because of sensor characteristics. Okay, very good. So let's start. Inertial navigation. So the reason why it's called inertial navigation is because we use sensors which respond to Newton's laws. Okay. So you consider an accelerometer or a gyroscope, and these objects have a certain inertia like all physical objects, and these objects, they maintain their velocity, either translational velocity for acceleration or angular velocity for the gyroscope. They maintain their acceleration and velocity unless they are disturbed by an external force. That is Newton's inertia law, right. So these sensors, when they make the measurements, when they are disturbed by an external force, this is why they are called inertial sensors. Alright, so what do they actually measure? Well, they measure two things. One is the translational motion, which is say the motion of this object as it is going in a particular line, right. So it could either go straight, it could go left, right, up, down, alright. It could also measure the rotational motion, and the rotational motion would basically be, I have this aircraft and I have an angular motion with respect to an axis, I have this rotation and I have the third rotation. We will see a little bit more about this. So since we live in a 3D world, we are always going to look at 3D translatory motion and 3D rotational motion, alright. Now there are various types of inertial sensors. The two sensors we will deal with in this and the next series of lectures are the accelerometer and the gyroscope. We could also be doing the magnetometer, but due to lack of time we will focus on just these two. So what does an accelerometer measure? Well, loosely speaking, it measures the acceleration, and the units of that is meters per second square, alright. An accelerometer is a very interesting object. So whenever we talk of accelerometers or gyroscopes from this time onwards, we will be referring to what are called as 3-axis sensors, right. And 3-axis basically means that because we live in a 3-dimensional world, we have motion along an axis, we can call it x-axis. We have a motion along a perpendicular to the x-axis called the y-axis, so that is in a plane. And then perpendicular to the plane we have the z-axis. In the literature they commonly do not call it as x, y and z, there are specific notations for this, we will see this a little bit later, but for now we only need to know that motion takes place in 3 dimensions, and each of these 3-axis sensors, they measure the motion along each of these axes. Alright, it could be a gyroscope, it could be an accelerometer as well. So I have also included some links for an accelerometer and for a gyroscope. Both are analog devices, but there are plenty of other options as well. There is InvenSense and there are Honeywell products and so on. This is just an example for you to see what these products are about. A gyroscope measures the angular velocity. Okay. We will see this a little bit later what I specifically mean by this. So the gyroscope is used to measure the rotational behavior of an object. The accelerometer is used to measure the translational behavior of an object. All right. Historically, accelerometers and gyroscopes would come as two independent products. For maybe the last decade or 2 decades, manufacturers have integrated these accelerometers and gyroscopes into a single device called a IMU. Okay. IMU is basically an inertial measurement unit. Okay. So, you have these small chips which we shall show you maybe in a couple of lectures with some experiments which one of my research associates Vinay Sridhar will be presenting. We will show you the basic IMU, which are the sensors mounted in that and examples of these. Okay. So, we are going to be working predominantly with IMUs which have an integrated accelerometer and a gyroscope on board. Okay, good. So, let us look at a little bit of dead reckoning in the very basic sense. So, this slide is basically on dead reckoning. All right. So, as I have said, the general principle of navigation using inertial sensors is based entirely on dead reckoning. Now, let us look at the example of accelerometers in this slide. In the next slide, we will go to gyroscope. So, what does an accelerometer measure? We saw that it measures the acceleration. Okay. So, here I have written, so let us say you have a 3-axis accelerometer. Okay. We consider a single axis, let us say the x axis, you could also consider y or z, and the measurement along that x axis will simply, we can denote it as we can denote the measurement along the x axis as simply ACC underscore x, and along the y which I am not mentioning here would be ACC underscore y, along the z axis ACC underscore z. All right. So, let us say that we have made a measurement along the x axis, and now we want to see how to compute position based on this. By the basic laws of physics, we know that the integral of acceleration is nothing but velocity, right. Inverse of that is derivative of velocity is nothing but acceleration. So, obviously, if you are integrating along the x axis, the velocity which you compute will be also along the x axis. Again, from basic physics, we know that the integration of velocity is nothing but position, all right, the position of the object. And as before, if you are integrating along x, the position computed will also be along x. So, that is basically what this expression over here says, right, which is basically the same as saying if you double integrate the acceleration, what you are going to end up with is the position x, right. We will do this. Okay. So, now that we have seen the basic say calculus of how we compute position from acceleration, all of you have done this in high school. Now, remember that our sensors are usually connected to microcontrollers, right, or to computers or to any electronic device. Being computers and microcontrollers, they can only take in discrete values of the actual data. So, if your real let us say this is time axis, this is the acceleration along, let us say the y axis, right. So, let us say the vehicle was accelerating in that particular manner. Okay. When you actually try to convert this or connect this sensor to a microcontroller, you need to pass it through a analog to digital converter, right, and depending on the resolution of the analog to digital converter, you actually get a 16 bit, 10 bit, 8 bit, so on and so forth, right. So, the accuracy increases with increasing resolution. So, with whatever accuracy with whatever resolution we have taken, we will be able to recover some parts of this data, right. So, the complete curve is a true acceleration. What your sensor is able to measure, okay, are these points. It cannot measure anything in between. unless you increase the sampling rate of the sensor and unless you increase the resolution of analog to the digital converter. All right. So, now in the discrete world or in the discrete time, so this is the continuous time. So, in the discrete time, which as all of you know are nothing but samples, how will this look like? The measurement, so I will call it ACCY, actually measured and then discretized and sampled. It will basically look like this, right. That is going to be your measurement. Now, this is the actual data which is going to come into your microcontroller. So, I would call this as say sample number 1, sample number 2, 3, 4, 5 and so on. Now, based on these measurements which we are taking, the acceleration measurements, our objective is to compute our position, right. That is the whole point of dead reckoning. Based on whatever you know in the past, you want to predict your future. So, based on the current acceleration, I would like to know what happens next, or a different way of putting, based on the acceleration which I have measured now, I want to know where exactly I am. So, you have to double integrate the acceleration. How do you do this in the discrete world? Because you are now inside a computer, your data has come inside your microcontroller or your computer. So, how would you actually compute this? Well, let us look at the basic equations first, right. So, we see that dv by dt, where v is the velocity, is nothing but your acceleration. Okay. So, let us just take it along the x axis. This is nothing but the limit Vx of t plus delta t minus V of t whole divided by delta t is equal to acceleration x. Okay. We know this from basic calculus, that the derivative is expressed as a limit delta t tends to 0, blah blah blah, so on. Now, of course, in the discrete world we do not have the delta t really tending to 0, it is really small, you know, it could be 0.01, maybe 0.0001 and so on, but it is never perfectly 0. So, let us fix the delta t to a certain value. Okay, we will just call it as delta t. It could be any number depending on how fast you are able to sample your signal, all right. So, we can remove the limit for now because it never really goes to 0 and you are left with this basic expression in the discrete time. How do I, if I expand this expression, I will basically get Vx of t plus delta t, okay, is equal to V of t plus ACCx times delta t, right. This is your difference equation which does the following. It uses the current information of the measured acceleration, note that this is a function of time. It uses the current velocity which is known from the previous calculation which we have done, and it calculates the next velocity. Okay. So, it predicts what the next position, the next velocity is going to be. Now, I have expressed this slightly differently in this equation over here. So, instead of t I have taken k and okay. So, let us see how this looks like. So, if I write this equation over here, this will basically look as follows. So, Vx of k, note that in my case I took t plus delta t, in this case I am taking k because I am doing a k minus delta t in the other place. So, Vx of k is nothing but Vx of k minus delta t, all right, plus acceleration x times k times delta t, all right. This is the same as this equation except that I have used a slightly different notation over here and here. Okay. So, we will not be using this notation so much. This is the kind of notation which you will see when you write your code and I will show you this a little bit later. For our discussion now we will use this notation, we will come back to this when I explain the code to you. So, this is how you compute the acceleration, the velocity from the given acceleration, all right. Now, how would we compute the position? in exactly the same way that we have looked at the computation of the velocity equation. So, now that we know what is the current velocity which we have computed by using the acceleration measurement, we are just going to repeat the same process for computing the position, and that again follows the same rule that dx by dt is nothing but v x, the velocity. So, this basically would say, if I write this in the notation of k's, it basically says x of k plus let us do it. So, x of k is nothing but x of k minus delta t, the previous computed position, plus the current velocity which I have computed from integrating the acceleration before, times the delta t. Okay. So, this is the previous computed position, this is the current computed velocity. Let me recall the previous equation of how we computed the velocity. So, there we had v of k was equal to v of k minus delta t plus acc x of k times delta t. So, in that case, again as we are seeing now, so this was the previous computed velocity, right. This is the current measured acceleration by the accelerometer. So, current measured acceleration by the accelerometer. So, this would be step 1, this would be step 2. So, you first compute the velocity based on the previous known velocity and the current acceleration, then having the value of this velocity, now you plug this into this equation for computing the position. So, the current position is now equal to the previous computed position plus the current computed velocity times delta t, okay, and that is basically this expression over here. So, this will just be x of k equal to x of k minus delta t plus that was wrong, we are going to take the velocity plus velocity which is computed at time k times delta t, right. So, these are my dead reckoning equations, which basically follows from the mathematical principle that if I double integrate the acceleration, I get position. To do that in a computer, you need to first integrate it once to get velocity, integrate that the second time to get position. So, these are the equations we are going to be using in our microcontroller programming, which I will show you tomorrow to compute the actual position. So, this is the translation position because we using the accelerometer data. What happens when we use the gyroscope data? If you want to visualize this, just think of this as, let us say there is a disc over here and it is spinning along this axis, okay. So, the disc will have some inertia, it will have some mass and so on, and you apply a torque on this disc and you rotate it, right. Say for example, I have connected a motor over here and I am continuously rotating the disc, and here if I place a gyroscope at this location, it is going to measure the angular rotation rate in the units of degrees per second, right. That is what the angular rotation rate is. Now, what I want to compute is the angular position. At every instant of time, I want to know where this disc is. I want to know whether I have rotated 5 degrees or 10 degrees and so on, given the measurement is angular velocity. So, of course, by basic physics we know that integration of angular velocity is nothing but angular position, and we use exactly the same story as before, since d theta by dt along the x axis of course is omega x. I will rewrite this in the discrete time domain, which we get after sampling the angular velocity data from the gyroscope. So, this will basically become theta x at the sample number k is the previous computed angular displacement, so k minus delta t, plus the current measured angular velocity, okay, which comes in from my gyroscope, times delta t, okay, and that is exactly what we have over here. Okay, so this is actually should be delta t, it is more a computer notation which I have used over there. So, this will come to later when we are looking at the code, we will consider this equation for now. Okay. So, we see again this is a first order difference equation because we only had a first order differential equation over here, alright. So, in both the cases for the accelerometer and the gyroscope, we compute the first order difference equations in order to get the angular position and the angular and the translatory position, alright. So, that is done, and now of course we have a slightly different issue, which is basically that each sensor, as I have said before, is a 3-axis sensor. So, what this specifically means is that let us consider an accelerometer. So, again I have explained this very briefly before, and let us say that you have a vehicle, let us say a car or something like that. It is a pretty ugly car, but that is good enough for our story. So, let us say you have a car and it is moving, it is moving on a terrain, right, it is not a straight road, it is moving on a terrain like an off-road vehicle in the Himalayas or somewhere. And let us say we have these axes which we denote with x, y and z. Now, if it is moving on only one direction, in only one axis, say it is a perfectly flat road. So, let us say it is moving only along the x direction. The 3-axis accelerometer, which can be visualized like this. So, this will be one axis, the other axis and the third one, each one is orthogonal or perpendicular to each other. So, this 3-axis accelerometer will measure the acceleration of the car only in the direction in which it is moving, right. So, it will not measure this direction, the acceleration measurement will be 0 in this direction, it will also be 0 in this direction, alright. It measures only in the forward direction in which it is moving. Similarly, if it is just moving left and right, say a plane or a helicopter moving left and right, along this axis over here, right. So, along this axis it actually gives me a non-zero acceleration, but along the forward axis it will show 0, along the vertical axis it will show 0, right. If you move in a combination of two different directions, both the x and the y axis measurement of the acceleration will show non-zero values. If it moves in 3D, all 3 axes will show non-zero values. Okay. So, that is what an accelerometer measures. A gyroscope in a similar way again has, so I can call this as ACC along x, ACC along y, ACC along z. A gyroscope will measure the angular rotation rate along with respect to an axis. I will give a brief idea of that now. So, let us say that I have my 3-axis sensor, okay. We will call this the one pointing say pointing towards you as a forward axis, the one pointing to the right as one axis, and the vertical axis completes the orthogonal system or the perpendicular axis system. So, I have got 3 axes all perpendicular to each other. Now, let us say I take this system and I rotate it about this axis, alright. How would I rotate it about the forward axis? I keep the forward axis fixed and I rotate it, right. So, you can see the motion over here. So, this motion is an angular rotation about the forward axis. What about a rotation about say the right side axis, the x, the y axis? So, I keep this one fixed and I rotate it this way, right. So, this is an angular rotation about this axis. Finally, I keep this fixed and I rotate it over here. This is another rotation about this axis. So, you have 3 rotations and the rotations are measured with respect to each of the axes. So, it would look like this. So, I have a rotation about the x axis, or I can have a rotation about the y axis, a rotation about the z axis, or you can have a combination of a rotation. So, it need not just be a rotation like this or a rotation like this, it can be a rotation like this, right, and that is a combination of all 3 rotations. Okay. When you take all of these, then basically what you will get are these 3 equations in the computer in the discrete time case, right. So, this is the computed position along the x direction, assuming we have computed the velocity along x, we have the position along y, position along z, okay. And similarly, we have the angular position along x, angular position along y, angular position along z after we have made the measurements along x, y and z, angular velocity measurements. For those of you who either watched lots of movies or played some nice video games like flight simulators and those, or read some crazy novels, you may immediately recognize that these 3 angular positions are very commonly known as the roll, the pitch and the yaw, alright. We will see this in the next slide. So, just small terminology, the word attitude in navigation, it does not refer to good attitude or bad attitude, it refers to these 3 angles we are talking about, the roll angle, the pitch angle and the yaw, okay. And note that each of these angles is a rotation about one specific axis. So, for example, the roll angle is usually called as the rotation about the forward axis. So, I keep the forward axis fixed and I roll my vehicle, right. If I keep the side axis fixed and I pitch up and down, so the pilot who is sitting in the plane, they pull on the you can call it the joystick, they pull on the joystick and the plane pitches up, you push it down, it pitches down, right. The final one is a rotation about the z axis, this is actually the heading or the yaw. So, you keep it over here and you ask the plane to move to change the direction to the right. So, it rotates to the right, left it rotates to the left about this axis, okay. So, that is roll, pitch and yaw, and you can see the small illustration over here. So, you mount your sensor at this place, the gyroscope, and this is the forward axis, this is the vertical down axis as it is called, and this is the right axis which completes the orthogonal axis system, okay. So, whenever you talk of roll, you typically talk of the aircraft rolling with respect to the forward axis. As you can see, my forward axis is not moving. When you talk of pitch, this axis does not move, so it's just a rotation like this, and the same for the yaw. This does not apply only to aircraft, it applies to cars, as you can see over here, because cars, especially off-road cars, when they move on uneven terrains, you have a roll, pitch and a yaw. As many of you would have experienced, if you take a car ride through, let us say, Bangalore's amazing roads filled with potholes, you often you go into these kind of roll, pitch and yaw. And of course, this applies to all movement. You can talk of human movement, right. So, as I am standing here, with respect to you, I may be doing a yaw, I may be doing a pitch up, my hand may be doing a combination of angular rotations and so on. Every one of this can be measured by the use of a gyroscope, okay. Fine. Now, attitude, okay. So, the roll, pitch, yaw. Attitude is good, but sometimes attitude is not good, and there is always a problem with attitude. Well, let us see what is the problem with attitude over here. Actually, it is not just attitude, I need to be more precise. attitude as well as the translational position or translational movement, you can call it. Okay, so let us say that one of you cool people are lying on a beach, wearing some dark shades, and you are just looking up at the sky, and you see a nice aeroplane flying across over here, all right. And there is this friend of yours who is sitting in another part of the town or the city, and you want to call up this guy and say, hey, look man, I saw this amazing the LCA Tejas aircraft, India's own fighter combat plane, brilliant stuff. Now this guy is going to ask, so the guy who is sitting in the town, he is going to ask his friend, dude, where did you actually see this plane? Now this guy is going to say, I saw the plane, let us say approximately 2 kilometers above me. This guy has no clue what it means by 2 kilometers above him. He does not know where he is, right. So the guy in the town does not know where the guy on the beach is. He does not know what 2 kilometers above him means, especially if this guy is sitting on top of a mountain and this guy is on the beach at almost at the sea level. So he has no clear idea of where the plane actually is with respect to him. The person on the beach knows where the aircraft is, but the person here, based on the information which the beach dude has given him, he is unable to configure or figure out where exactly the aircraft is. There is a further problem. You have the aircraft shown over here, okay. Now of course we need the aircraft flight control system needs to be able to compute its own position. So it places these gyroscopes, accelerometers and all these things in the aircraft. Now where does it place it? Let us say for example it has placed it, let us use a different color, white. Let us say it has placed it over here, okay. So this box, it is actually a very small box, is placed over here, and this box is actually going to do the measurements of angular rotations as well as accelerations, the IMU. Now what is the problem with this? As you can see, the aircraft axis is shown over here with the roll, the pitch and the yaw, and aircraft axis is typically defined with respect to the center of mass of the aircraft or the center of gravity of the aircraft. The IMU in this case is placed at a slightly different location and it is not aligned with the aircraft axis. So if the aircraft axis is like this, the IMU axis could be like this, right, because it depends how I have placed my aircraft. So if this is an aircraft, very bad example, I agree. If this is an aircraft, let us say this is the IMU, okay. If I place it perfectly aligned with the axis of the aircraft, that is good, but because of various reasons I have placed it like this and the axes are completely misaligned, okay. So in that case the axis of the IMU will be like this, that would be the forward axis, this would be the pitch axis if you want to call it, and that would be the vertical axis, and you can see the two axes are not aligned at all, which means the IMU which measures the aircraft acceleration and angular velocity, it is measuring it in its own frame of reference, right, the 3 axes of the accelerometer. With respect to these 3 axes, it is telling the aircraft is rotating about a certain degrees per second, but the aircraft is in a different axis representation. So the aircraft is in this axis representation, the IMU is in a different axis representation, all right. So you essentially have now a bigger problem. A guy, the pilot in the aircraft, if she or he looks at the data coming from the IMU, so let us say the data coming from the IMU is displayed on the screen of the pilot and it is saying that, look man, let us say your pitch angle, okay, is currently going like this. Now the pilot is not really sure if this is correct or not, because this pitch angle is measured by the sensor and it is not the same as the actual pitch angle of the aircraft because it is in a slightly different position. For all you know, If this is on my left hand, this is the aircraft axis, the right hand is the sensor axis. The way that the designers mount the sensor on the plane, it could be completely 90-degree shifted. So, the pitch axis becomes the roll axis becomes the pitch axis. So, when the pilot is looking at the data from the pitch over here, it is actually the roll axis of the aircraft, and if the pilot has to make a decision based on that, it can be catastrophic. So, this is a problem with reference frames, the problem with attitude, problem with translation movement. Every object which measures movement measures it in its own frame of reference, its own axis or coordinate system. The actual system, the plane or a robot or a human walking, is experiencing motion in its own reference system. Okay, so typically you have the system, which could be a plane or a fancy robot, a human being walking, and so on. This has its own frame of reference, its own coordinate system. This is called the body reference frame. It is called the body reference frame. A sensor which is mounted on the body, okay, to measure the motion of the body, or you can actually say there is a camera over there and it is capturing my movement. The camera is recording my movement, or the sensor on my body is recording my movement in its own reference frame called the sensor frame. And then you have an observer like you or me standing outside and just watching this cool plane flying above. Then you have an observer frame. Now, with three different frames, how are you going to say the aircraft is exactly there or the robot is exactly over here? Autonomous robots which are wandering all over the place, like these Terminator movies. How would you say that the Terminator is right over here? You can only do that if there is a standard reference frame, and this is actually a very important problem in robotics, in ship and aircraft navigation, human movement, everything. Every movement must be expressed with respect to a standard reference frame. It cannot be expressed with respect to his reference frame or her reference frame. It should be with respect to a standard reference frame which everyone understands. Okay? However, measurements are done in the sensor frame. The body is moving in its own frame. The observer has his own frame. So, what we will need to do is whatever measurements are done in the sensor frame, we need to translate it or we need to transform it into the standard reference frame. Whatever the body is experiencing, transform that into the standard reference frame. Then you know exactly what is happening to the motion of the object. All right. So, this is the problem which I have been talking for the last 2-3 minutes. And the way that people address this problem in navigation is when a sensor measures the acceleration and angular velocity in all three axes, we transform the measurements usually first into the body frame, into the aircraft or to the robot. So, we know exactly what is the measurement of the aircraft movement. We do not care what the sensor is experiencing really, we care what the aircraft is experiencing, specifically the movements, right. So, we transform the sensor measurements into the coordinate system of the aircraft or the robot or the human being who is walking. Once you are in the body frame, of course, your body frame is different from his body frame, right. It's the body coordinate system is different from his body coordinate system. So, you need to now transform it into the standard reference frame. Okay. So, for each of these transformations, you have something called a rotation matrix. So, apply the rotation matrix and you actually go from one reference frame to another reference frame. Okay. We will see now one simple example of how to actually do the rotation matrix, then we will go to the complex 3D case. Okay. So, let us see how we can do this reference frame transformation. We will start with a very simple example, but let us frame the question properly. So, the question would actually be, given a motion which is measured in one reference frame, let us say it is the sensor reference frame, okay, how would you represent this motion in another reference frame, let us say the body reference frame, alright. So, that is the basic question which we are asking. Okay, we will actually pose the question as follows. So, given a motion which is measured in one reference frame, how would we represent it in another reference frame? We always have to keep track of two quantities. One is the translation, the other is a rotation. We will focus primarily on the rotation over here. I will briefly explain how to take care of the translation afterwards. Okay, so we have two reference frames, as you can see here, the sensor reference frame and the body reference frame. We need to represent one in terms of the other. Let us take a very simple 2D example. Okay, and in this 2D example, I will assume I have got a vehicle and the center of gravity of the vehicle is over here with the axis as follows. So, I will call this x body axis and y body axis. Now, what I have done is to mount IMU at exactly at the center of gravity of the vehicle. Now, usually this will not be the case, and if it is not the case, you need to take care of the translational part as well. If you mount it exactly at the center of gravity of the vehicle, you only have a rotational problem, which is what we will deal with here. So, let us say we mount the sensor like this, okay, and the sensor origin coincides with the origin of the body coordinate system, except that the sensor is misaligned, okay, with respect to the body coordinate system. So, the sensor coordinate system will be like this. Okay. I will call this as well, let me rewrite that a little bit. I will call this as x sensor and this is y sensor. So, you can see that the two origins are perfectly aligned. There is only a difference in the rotation between the two sensors, and it is intuitively very clear already by now to most of you. All you need to do is to merely rotate the sensor reference frame by a certain angle to match with the body reference frame, alright, and that is exactly what the 2D example is all about. So, let us say that in the sensor reference frame, the xs and ys, I have said with respect to the origin, of course, we can call it 0 comma 0, it does not really matter, it can be any x comma y, because the two origins are perfectly aligned. Now, with respect to the origin, let us say I have measured a certain motion which is over here, and this could be acceleration, it could be angular velocity, whatever it is, depending on whether I am using an accelerometer or a gyroscope over here, any one of the sensors you can assume. And you see that any point in this is a measurement with coordinates, and it can be called as xs1 and ys1. Okay. What is xs1 and ys1 with respect to the origin? It is simply a vector, right, basic high school physics. So, this is the measurement which is done. I need to now take this vector which is the sensor measurement xs1 and ys1, and I need to transform this into the body reference frame, because I want to know in my body reference frame what is the measurement which I am seeing. I do not care what is in the sensor reference frame, I want to know in my body reference frame. So, given this, how do I transform it into the body reference frame? Very simple. So, we have the two, this is the sensor reference frame, and then you have the body reference frame, right, xb and yb, this is xs, ys. Now, you need to know only one important quantity in the 2D example, only one quantity, which is what is the angular displacement between the two reference frames. That is all. I mean it's intuitively clear to all of you by now what it is that we need. So, if we know what is this angular difference, okay, let us just call it theta. If we are able to measure this theta, we know exactly what we need to do. Well, let us say our gyroscope is actually able to measure this theta, or we know from a third sensor, or we have manually measured it ourselves, that the two axes are slightly deviated with respect to theta, and you can actually measure this, right. So, you can actually put some sensors over here, and you can say that there is a angular displacement between these two reference frames. Once you know that, you are just going to do the following. So, given x sensor 1 and y sensor 1, okay, I want to express this in my body coordinates, right. I want to know what is x body 1, y body 1, and the way you would do it is really simple. You would actually do it as follows. So, x body 1 would be nothing but x sensor 1 times cos theta. Y body 1 would be nothing but y sensor 1 sin theta. And how do you express this as a matrix? Very simple. So, I would just put cos theta over here, 0 0 sin theta. That is it. So, when you do this, now I have a measurement in sensor frame. Now, I am able to express the measurement, the sensor measurement in the body frame. Brilliant, simple, straightforward in the 2D case. The 3D case becomes a little bit tricky, but it is almost the same logic. How we do that? Well, as follows. In the 3D case, note that you can have a rotation about all three axes. So, if you look at the previous slide, we basically said that there was a rotation of theta degrees about the x axis, which means even the y axis will also be theta degrees rotated with respect to the other y axis, right. So, what I am basically saying is, if this is theta degrees over here, by the property of orthogonality or perpendicularity, this will also be theta degrees, exactly the same, because both axes are orthogonal for both the reference frames. Not true for 3 axis system, it is a little bit more involved, and the reason it is a little bit more involved is as follows. 2 reference frames, let us take the forward axis, okay, this one over here, and let us say that you have a slight yaw of the second reference frame. Yaw is a rotation about the vertical axis, right. So, the above the vertical axis, the second reference frame is slightly yawed, okay, by some angle gamma. Now, because it is 3D, this is not the only case which we can have. About this axis over here, which I am showing with my left finger, about this axis I have a slight pitch, okay, with respect to this guy over here, and now I still have a third axis left, the forward axis, the roll axis. I have a slight displacement with rect. So, I actually have to now consider 3 angles, because my axis can be misaligned with respect to this axis in 3 different ways. I can have a yaw displacement, I can have a pitch displacement, and a roll displacement. All 3 conditions have to be considered. It's not difficult, it's fairly straightforward, you just need to use the correct math. Again, we take the same example of the sensor frame and the body frame, but please remember you can use this for any 2 frames, okay. So, the assumptions I am making here is that the sensor frame and the body frame have the same origins. So, in that case, okay, so we have this origin over here, the 2 reference frames. because we have three possible angular displacements between the two reference frames, we are going to consider each angular displacement independently. So, first in this particular example I am taking, we will assume that the sensor frame is rotated by an angle gamma, right, over here, okay, with respect to the body frame, with respect to the z axis of the body frame. Okay. Turns out if you do the math properly, because when we are doing a rotation about the z axis, notice that the bottom one is fixed. So, when you rotate about the z axis, okay, the third component, which is the z axis component, will all be zeros except the z axis itself, because the z axis is fixed, it is not moving, it is the other two axes which are moving, right. The other two axes by standard trigonometric relationships will follow this relationship. You do not need to worry about the derivations of this. Maybe those of you who are going for higher studies, you can study this later, not too relevant for now. It is important to know that if I want to go from the sensor frame to a frame called B1, which is body frame 1, where the z axis are now aligned. So, remember I had three misalignments, a misalignment about the z axis, misalignment about the y axis, that is a pitch axis, and about the roll. Let me correct these one by one. So, first let me correct the z axis. So, I do a rotation about the z axis, this one over here. So, that rotation I do first. The second rotation, which I will show in the next slide, will be about the pitch axis. So, I will do like this, and the third rotation will be about the roll axis. So, I am going to do this step by step. So, about the z axis, if you blindly go ahead and use this expression, okay, this is called the rotation matrix, and this rotation matrix helps you in this example to align, sorry about that, it helps you to align the two z axis of the two reference frames, that is all what it does. So, which means that if I have a vector, my measurement xs, ys, zs in the sensor frame, this I can use this rotation matrix and bring it to the body frame where the z axis of the two reference frames are aligned. We still have to take care of the other two reference frames. So, this is step 1. Step 2, let us say that your body frame was now rotated by some theta about the x axis. Okay. In the previous case it was gamma about the y axis, now theta about the x axis. Okay. In this case again, since it is about the x axis will always remain, all terms will be 0 and x axis itself will be fixed. So, it will always be 1, and we look at the rotations in the other two components, and it has a very similar structure as the previous one. So, this is again my rotation matrix, and notice what it is doing. In the previous example we had this rotation matrix with the notation RSB1, which means it is a rotation or a transformation from the sensor frame S to the sensor frame B1 where the z axis are aligned. In this slide we have RB1 to RB2. This is a rotation from B1 reference frame to B2 reference frame where the z axis is aligned as before, and now we are aligning the x axis as well. So, now two axes are aligned, and you can see that over here, right, both the axes, the z and the x are aligned after you apply the rotation. And again this is a standard expression. So, the measurement in body frame 1 where the z axis were aligned is now transformed to a measurement in body frame 2 where x and z are both aligned. Okay. That you can see in this slide. After the previous two transformations, the z and the x are now aligned with the respective reference frames, and what is left out is the y axis. So, let us say you had the angular displacement by beta with respect to the new y axis, do exactly the same thing as we have done before. So, we have had from the sensor frame to body frame 1. After this, we have done body frame 1 to body frame 2. In this case, we align the z axis. In this case, we have aligned the z axis and the x axis. And now finally, we look at the rotation between the two y axis of say body frame to the final correct body frame B2 to B. And now all three axes will get aligned, x axis, z axis and the y axis, and you can see that over in the next slide. So, when you rotate this by the appropriate angle, all three axes will be perfectly aligned with each other, right. So, like so, and this is the rotation to go from B2 to B, the second body axis to the final body axis. And interestingly, all you need to do in order to do this very complex sounding mathematical description is one very simple operation. Take the three rotation matrices and multiply them in this specific order. On the right hand side, from the sensor frame to body frame 1, that is one rotation matrix, multiply that with body frame 1 to body frame 2, the second rotation matrix, and finally multiply that result with the body frame 2 to the actual body frame, the third rotation matrix. You actually do that multiplication and you get this horrible looking expression which you do not need to worry about considering you are an undergraduate student. You can actually use this as it is, and this follows from very basic trigonometric rules and really nothing more than that. Okay. So, the interested student can contact me or on the forum, NPTEL forum, or you can look up in Google to find out how you actually derive these expressions. Okay. Now, this means, so this formula, what it actually means is this. It means that any measurement I do in the sensor frame, so I can call it xs, ys, zs, any measurement done in the sensor frame, if I multiply it with this rotation matrix, I will exactly get what the actual measurement is in the body frame. Now, the body and the sensor frame are aligned, they know exactly what they are both talking about, like where the vehicle actually is when you just multiply with this, which is this matrix, alright. Now, note that I have talked only about rotation, I have not talked about translation. Well, translation is slightly different, it is even simpler. So, let us say that you have two rotation frames like this and a second rotation frame over here. Origins are not aligned. That is the basic difference between the example considered here and the example I am now considering. Well, how to handle this? Really simple. So, this example we will write down over here and it is really straightforward. How we are going to do this is as follows. So, again we have the measurement in the sensor frame ZS. Okay. The first thing we are going to do is to align the rotation axis. Okay. So, by multiplying with our matrix which we have already computed. After doing that, we shift. Okay. So, I will actually draw this over here. This is one sensor axis, okay, and this was the other sensor axis, the body axis, let us say. Okay. Now, what we are going to do when we apply RS to B, this axis over here, okay, it gets shifted, displaced rather, angularly displaced to this axis. Okay. So, now the angles at which the two reference frames are being considered in are exactly the same. What is missing is I need a translation from here to here. I need to go I need to shift the origin from this place to that place. Now, let us not worry how that is actually calculated. Let us say someone actually tells you by measurement. So, you have your car and this is the center of gravity, and you have placed your so it is in some x, y, z body position origin, and you have placed your IMU over here. You can physically just measure it, right. So, you know that this is some x1, y1, z1 where you have placed your sensor, and you know the difference between x and x1, you know the difference between y and y1, z and z1. Subtract out those differences, and all you need to do is to add that small difference. So, I will call it x difference in the translation position, y difference in the translation position, z difference in the translation position. If you add this to the rotated values, you are going to get perfectly xb, yb, zb. So, first take care of the rotation between the two axes, then align the origins. Done. You are essentially done 3-dimensional inertial navigation. So, let me try to summarize this entire story which we have been talking about, which may seem a little bit complex when you encounter it the first time. If you go through this 2 or 3 times, it is actually fairly simple. All we are doing is really just trigonometry in 3D. Okay. So, let me just try to summarize it as neatly as possible. So, the problem was as follows. So, given 2 reference frames, let us call this as the body frame, okay, and another reference frame is the sensor reference frame. Now, we know that a measurement is always done in the sensor reference frame. The sensor measures values with its own 3-axis reference frame, which needs to be converted to the body measurement frame. Okay. And then of course, we need to convert the body measurement frame to the standard reference frame, but we will come to that later. So, how do we actually do this? Well, as we have seen, there are 2 steps. The first is align the axis rotations, okay, align the axis of the 2 reference frames, that is so if you align the axis of the 2 reference frames, even though they are widely separated from each other. So, as you can see, this is angularly different from this one. Let us first align them together, all right. Now, to align them, you only need that one R S to B matrix, you know, that big 3 cross 3 matrix which you had. You only need 3 angles, as you saw there was a gamma, a theta, and what was the last one, a beta. So, if you have these 3 angles, you can actually align the reference frames together, angularly align them. How do you compute these gamma, theta and beta? There are various techniques. For our case, let us actually suppose that we do it manually. So, as I said before, you have a vehicle with the center of gravity over here and the sensor mounted over here with its axis like this. All we need to do is to find out what is the angular displacement between these 2 things, all right. There is a bunch of ways of doing it, but we can just literally do it manually. I mean, if you are really lazy, just take a protractor and try to align them, and that will be reasonably accurate, right. If you want very high degree of accuracy, there are really fancy techniques, but let us not worry about that. So, all you had to do was to compute the RSB matrix and then multiply the vector, the sensor measurement that you do with the RS to B matrix. Then you get the measurement in the body coordinates with axis aligned. So, this is the axis angularly aligned body coordinates. It is still not aligned in the translation way. For that, all you need to do is to just compute this guy. So, if you know the x1, y1, b1 of the body, and you know the x2, y2, b2 of the sensor, it's again very easy to do. The easiest way to do it without actually breaking your head too much is to assume the body axis origin is 0 0 0, just assume it 0 0 0, no worries. You compute the displacement along the x direction of the body to see where the sensor is. So, if the body is over here, let us say this is the origin, alright, origin of the sensor. You basically just go along the x direction and you measure and you get the displacement delta x with respect to the sensor, the x displacement. Same thing do with y. So, keep going until you see what is that y, and the same thing with z. Then all you need to do is to add the delta x, delta y, delta z. This is the displacement, the translation displacement between the origins of the axis. And once you do all that, you get a completely aligned reference frames, and whatever you measure in the sensor axis, now you know it is exactly the same as what you actually have in the body axis. Okay? That is a basic principle. You are free to contact me if you want specific code for this, if you want more explanation, literature about all this, you are free to contact us on the forum. Okay. While this is fairly simple, there are fortunately or unfortunately, there are too many reference frames which are actually in use. So, while we like to say that there is one standard reference frame, it really depends on what your purpose is. If you are on Earth, one of the standard reference frame is called the Earth centered inertial reference frame, where the origin of the reference frame is the center of mass of the Earth, and one axis points towards north, other axis point towards the vernal equinox, and the third one just completes the right angle triangle along the equator. So, this is one reference frame. So, anywhere you are on Earth, right, can I see India here? No, I can't see on the map, but okay. Anywhere you are on Earth, you can define your position with respect to these three axes, and actually this is what will give you the standard latitude, longitude and altitude measurements. But this is if a vehicle is on Earth, but for a satellite you have a different reference frame altogether, and one of them is called the orbital coordinate system. If you are inside a room like the one that I have, it really makes no point to worry about orbital coordinate system, and for very specific applications you may not even care about earth centered reference, earth centered inertial frame. You may just literally worry about this room axis. How do you define the room axis? I can just take one corner of the room, I go down where all the walls are meeting at one corner, and I can define that to be the origin. Okay? So, reference frames are very important, and it is up to you to decide what reference frame you want. You can choose a reference frame of this room. Assume your robot is navigating within this room, its only job is to worry about what it is doing in this particular room. A person outside who wants to monitor the robot is also interested in what the robot is doing in the room. We do not really care if this room is in Chennai or Bangalore or Mumbai or wherever, right. It is enough for us to know that in this room the robot is doing its job properly. For that you just need a room reference frame. I can take the axis over here and then define it. If you are going from actually I am planning a trip from Chennai to Mahabalipuram tomorrow, because you know I am visiting Chennai from Bangalore, then my room reference frame is of no use, my car reference frame is of no use. I really need a earth centered inertial reference frame. I need a GPS kind of reference frame, the latitude, longitude, altitude, that is more relevant for me. So, what you use, how you use is up to your task. In all cases, the way that you would compute the way that you would express a motion in one reference frame in another reference frame is exactly by the story which you have described. This was the basic story of, say, navigation, where we discussed different navigation techniques. We looked at very briefly what is dead reckoning, which was basically the integration process, and we represented that integration process with the difference equation which is going to be implemented in a microcontroller, and finally we concluded with reference frames. In the next lecture, what I will be talking about is one of the most important or the most important problem in dead reckoning. It is a problem called drift, and we will see that drift arises because of certain noise characteristics of sensors, and very briefly I will introduce one or two techniques of how we can remove this noise in order to get a better computation or estimation of position. All right, and we will finally conclude with a very nice detailed experimental example right here. My research associate Vinay Sridhar will actually be taking care of that. All right, thank you very much.